Okay, so in the last lecture, we have calculated the modes of a lattice in a very general manner. And we know that for a d-dimensional lattice, we have the acoustic phonons, and if the unit cell is larger than 1, we have also, let's say we have p atoms per unit cell, we have p minus 1 times the optical modes, where optical means that if k goes to 0, omega doesn't go to 0. Okay, so we started this whole game by saying something about the heat capacitance of a lattice. We calculated it classical, and if we continue and estimate the classical contribution of the modes that we have calculated, we get exactly the same results because it doesn't depend on the details. It's just half kT per degree of freedom. We still have the same number of degrees of freedom as well. Nevertheless, when one goes and measures the heat capacitance, especially at low temperatures, it doesn't fit the classical prediction. Now, clearly, we need here a quantum contribution. So, how do we quantize this, these modes, these elastic modes that we have calculated? Phonons. The answer is phonons, and the real answer is, sorry, not in this course. You'll do it in advanced quantum mechanics.
In statistical mechanics. The bimodal?
Yes, but you didn't do it. Okay. I'll insist that you didn't do it. Why? Because you didn't quantize a field. This is a field, and you don't know to quantize a field. So, fortunately, in order to do statistical mechanics, which takes into account the quantum results, we don't need to know to solve exactly this Hamiltonian, which we solved classically. It's enough to note that we have their modes, and these modes don't depend on each other, they're independent, and they originated from Hamiltonian that was quadratic in form. Once we know that, we actually know how the energy spectrum of such a system behaves without being able actually to specifically write down the wave functions or things like that. Okay, so what is the result? The result is very similar to photons. Or if you want another way to look at it, it's very similar to the solutions of a harmonic oscillator. Again, not very surprising because in the basis of our assumptions, we developed our Hamiltonian around the equilibrium positions, and that's quadratic. Okay, so just a couple more words on why I'm insisting that you don't know to solve it. When you do nowadays, after you finish 2 courses in quantum mechanics and write down Schrödinger equations and solve it, get eigenvalues, eigenvectors, know to calculate the expectation values of any operators that you're given, why can't you solve such a problem? When you're writing down a wave function in Schrödinger equation, what is the first thing that you check?
Probability?
Hermitian,
Excuse me?
that the operator is Hermitian.
Yes and yes, but that's not the first thing. You are given a wave function. What do?
Normalize?
Normalize. You check that the probability of finding this particle anywhere in the system is equal to 1. What does that actually mean? The wave function has to be normalized for any t, right? You never have run into a situation where you start with a particle and after some time it disappears. It's not there. But phonons and photons and other particles have no conservation. There's nothing stopping them once you have a photon for it to be absorbed. You actually did probably some problems where you start from the electrons in the atom absorb a photon and it moves to a higher energy state, right? That's how you get a spectrum. But at the moment you don't know to handle any problem where the number of particles is not conserved. Why Schrödinger equation works so well for most situations that we're trying to describe? Because unless we are dealing with very high energy particles, for example electrons, they are not created and not annihilated.
Can we look at it like a grand canonical system?
Exactly. You treat quantum mechanics as a grand canonical system, but then basically you have to write down your Hilbert space in a different way. Why? Because exactly as the difference between a canonical and a grand canonical ensemble, your probability is not one that you have one particle, as in the Schrödinger equation. You have some probability of having 0 particles, 1 particles, 2 goes up to infinity, and the sum of the probabilities on all these states sums up to 1. But if you're looking on a certain sector of this Hilbert space, no, it doesn't have to be 1, and with time it could change. Energy is conserved, but you could change 2 low energy photons to 1 higher energy photons. There's no limit on it in nature. This kind of Hilbert space has a special name, Fock space, and you'll study all of it in advanced quantum mechanics. But it needs a few lectures to introduce it, and it's not in the curriculum of our course. So, as I said, nevertheless, we can treat our problem of heat capacitance without understanding anything about this. The only thing that we have to understand, what describes the quantum state of this system. So, what are our classical degrees of freedom? Well, we can say the position and momentum of each part of each atom in the lattice, but we didn't work so hard on this mode representation to go back to this representation. Basically, all we need to know in order to describe the quantum state of the system is the number of phonons for each given k in the system. Now we understand that we can have branches, we can have a few acoustic branches, we can have optical branches, so I'll add here S. So this is wave, vector or number or how you call it, and S is so when I want to describe the system quantum mechanically, I just come with a very long list of there's two phonons at k equal pi over NA, the first one, second one, the third one, and so on and so forth. And if we have branches on the first acoustic branch, on the second, on the third, on the fourth, and so on and so forth. Actually, this shouldn't be surprising to you. You solved the problem of harmonic oscillator. And what did you see there? To describe it classically, what are the parameters?
You diagonalize the matrix and get...
No, but what are the parameters? The degrees of freedom. X and P, right? Two numbers. One dimensional, so it's really two numbers. I work, I take the Hamiltonian, I transform it to creation and annihilation operators, and I end up with one number, which is n. Right? Everything else you can pull out from this number. Same here. If I had a three-dimensional system, let's assume only one atom per unit cell. I started with 6 numbers, px, py, pz, x, y, and z. And I end up here, I have 3 branches and one number for each k. What is the big difference between harmonic oscillator and this problem? Is that you have different values of k. In the harmonic oscillator, you had just one. Okay, so same way that I write the energy for a harmonic oscillator. This is exactly the energy for a harmonic oscillator. But I have to take into account the fact that I have different oscillators for different k's, and the value of omega is different for each k and for each branch. From where do I take it? From the classical solution. That's exactly the dispersion relations that we calculated in the previous lectures, where we got omega as function of k. It exactly plugs in here. How do I turn this? Once I have spectrum, I can do any statistical mechanics on the system. I know the states, I know their energy. Once I know these two things, I can do everything in statistical mechanics. Okay, so let's say, how do I calculate the free energy? Why per unit volume? Because if I'm dealing with an infinite lattice, which I'm dealing here usually, the answer to what's the free energy doesn't require any calculation. It's infinite. So therefore, what is interesting is per unit volume. So V is the volume, and I have to sum up over a logarithm where EI is the energy levels of the system. Here, of course, I will replace I with K and S. Questions?
למה אנחנו לא עושים את זה פעם פר חלקיק ולא עושים את זה פר זו?
Because I don't have here per particle, because particles are not conserved. So I take a volume of the system. Okay, so let's write it down explicitly. Yeah. Just wait a minute, I want to, I have not written it. I'll do it in 2 steps. what does this mean? Every state is described by a vector of numbers nks for the first k, for the second k, for the third k, and so on. And I have to explicitly give the number nks for each one of them. Okay, and then what is the energy of this state? Because a state is described by the set of numbers nks. So give me a state, and then I have to sum up over all the terms here, because that's the general, this is the accumulated energy of the whole system. And that's a state of the system. I wanted to do it in 2 steps, not to throw immediately in the multiplication, so it will be clearer. Okay?
Charles, but here you treated it like a canonical ensemble, not a grand canonical. Because it's E minus beta EI, and in a grand canonical there's supposed to be a mu n, right?
I'm now looking at basically all the possible states. I didn't put in here. When do you treat it with a mu, with a grand canonical ensemble? If you want to have some average of number of particles in it. I didn't specify here anything like that. Okay. So since it's a summation of things in the exponential, I can change it into a multiplication of separate contributions for each k and s. So I'm using the notation k1 s1, k2 s2, all the possible states of the system, and so on and so forth. So, and here of course I forgot the lab. instead of summing up all the different possible NKS, I can sum over the first possible NKS, and then over the second, and then over the third, and so on and so forth. Now, Ks is just an index that I run over. And this I know how to perform. Because it's just usual geometric series. Okay, questions still here?
How did we separate the omega k and the NKS for what they were here to the NK1S1, NK2S2 and all that? It's like a...
I just wrote this summation explicitly.
Oh, okay. So I see. Okay.
If you have a sum of terms in the exponent, you can always write it as exponent of the first term times exponent of the second term, and so on and so forth. So that's all I did here. And I got to this point. Heat capacity minus, of course. Okay, so let's start this way. If I have a line of a multiplication,
Summation of lines.
it's the summation of lines. Okay, so I'll write another step here. F is equal 1 over V summation of K and S two okay. So let me write a sidebar just to do the derivative. Someone should screen it means that it's divided by 2. Okay, regular derivative. So you remember what, I assume that you have seen it already in statistical mechanics.
Yeah, we saw something like this.
Not something like exactly. So what do we do to get something concise and no, we multiply it by EH bar over KS divided by 2 plus and by 1 minus E H bar omega Ks, and we get the solution. Another minus here. This is a form you're well versed with. This is the probability of occupation of a boson at a certain omega of K and S. This is times its energy. And the derivative, of course, of F2 beta is the energy up to a minus sign, so we get rid of this minus, so I'll write it down the final form. Put it. This is a probability. Okay, so why did I put here tilde? See, we started by saying that quantum mechanically I decide what is the state by giving the quantum numbers nks. We have in the first one 3, in the second one 5 phonons, in the third one 7 phonons, in the eighth state 0 phonons, and so on. A vector of discrete numbers. We did here statistical mechanics, and we ended up with some average value of this occupation, which now can get any value between 0 and infinity, and it doesn't have to be an integer. So in some sense we lost quantization when we're going into the statistical description, because in the statistical description we have already averaging over all the possible states with some probability. And this is what this tilde is trying to remind us. It's not the same NKS that we had here. Okay, until here, all of this you have studied in statistical mechanics. Maybe forgot, maybe it was completely unnecessarily, and I could have written this result and tell you, go back and refresh yourself on the results of statistical mechanics, but I think there is some value in seeing things again and again until it becomes second nature. Okay, so I have U. What do I have to do in order to get heat capacity? Derivative by T. That's all. That's all with a caveat that we'll be stuck with the sums that we have to perform. Okay, let's go into the limits here. Because it's not easy to do it for any value of beta. What is this limit?
High temperature.
It's the high temperature limit. And what do we expect?
3.5 kBT for whatever degree of freedom.
We expect here to return to the classical behavior. If the energy, the temperature, meaning the average energy per degree of freedom is so large that it's much larger than the quantization, there should be no remnant of the quantization. Okay, in order to shorten our notation, I'll define x as T, meaning, and what does this mean? That we are at the limit that x is small, just by definition. And So I wrote it down as a Taylor expansion. Pulled out X and another Taylor expansion that 1 plus x to the power minus 1 is just 1 minus x, so I wrote it down. And I use this approximation here. So basically, in the first order, we're back to the classical result as we expect, and we can even get the first correction. What is the result of this summation? Well, depends on the system. What is the dependence of omega on k and the number of branches? Okay. What happens in the opposite limit? This is something that you can't do in your notebook.
רק השאלה השורה האחרונה בבקשה.
Sure. Give it time to write it down.
למה מדי פעם אנחנו לא רושמים חצי מהאס? מדי פעם אנחנו כן רושמים?
Now, S
נראה לי שלפני כן היה וקטור S ממש.
S shouldn't be a vector. If there's anywhere that has a vector, it's wrong because S is just a number of the branch.
Okay.
K has Kx, Ky, Kz. Okay. So, what can I do here? Well, first note that if the temperature is low,
Then the exponent is really big, and you can take care of the one.
even before that, there's a very important simplification that I can do even before doing anything with a mathematical expression. It's concerned with this index. Well, if you remember, we have acoustical and optical waves. If the temperature is very low, no optical mode could be excited just because you have to put a large h bar omega into them, meaning you'll never have enough energy at low temperatures to excite them. Therefore, their occupation is zero, therefore they're not in the game. So, what can I say? I can say that S sums only over acoustical waves, modes, and instead of writing omega ks, which we left unspecified, if it's an acoustical wave, just Cs, which is the velocity of this specific mode, times k. That's the definition of acoustical waves, at least at small k's, and since we are dealing only with small t's, only small k's are really of interest to us. Okay, so far so good. So now I'll do S now. The sum over S is only on the acoustical waves. I'll change the summation into an integral over k. Not completely kosher, but not too bad. Usually I think of a large lattice where large n is much larger than a huge number, and therefore 1 over pi. Pi over n times k is very small, so I can exchange the summation by an integration. And we'll write down explicitly okay, where d omega is angles that we have there. I went over from a Cartesian description of k as kx, ky, kz to vector k defined by its length and by two angles, and since in the acoustical mode the angles don't have any influence on the energy, I can just perform the integration here and get 4 pi. And let's simplify our writing by just to get something shorter to write here. Okay, and could someone guess what is the additional simplification that I did?
Gamma function, maybe?
No, I didn't. All I did here is instead k, I have k squared from the Jacobian, another k from here, k to the third, that's why I have x to the third. Why I have here kb to t to the fourth. 1, 2, 3, 4.
You change variables.
I change variables and I get here a power of 4 of kbt. And the only thing that I massaged a bit is instead of writing c as function of the branches 1, 2, and 3, I multiplied by 3 and entered here an average value of c. So that's the reason why I have 3 here, and c lost its s, because I'm just writing down the average value. Not completely kosher, but not too bad. What's nice about this, why I'm working here with a dimensionless variable, is here it's very important what CS sits in the exponent. When I pull it out, it just becomes a prefactor. And there I can average easily, and if you want to be very exact, so it's 1 over C3 is equal to 1. S omega 4 pi 1 over CS. That's exactly the averaging procedure, but not, let's say, it's not very important. Okay, so one good thing that I got here is that the only dependence in t is here, not in the integral. That makes life easier. But on the other hand, you still have to evaluate the integral.
Because the variable you chose depends on t originally,
Mm-hmm.
that doesn't change the result. Because you took it out of the equation because
No, mainly because I have here an integral between 0 and infinity.
okay.
If I would have a different kind of integral with finite range, so it changes also the limits of the integral and makes life much more complicated. That's the reason that many times in physics, if the boundary of the integral doesn't change much, we take it to infinity, it makes life much easier. Good. So I'm left with the integral. Okay. Okay, what did I do here?
You turned the denominator into its Taylor series.
No, it's not even
Geometric series.
a geometric series. The result of this geometric series is simply this. What did I gain by it?
Yeah.
This integral I know how to perform. So I'll move from integrals that I didn't know to perform to a summation of a series. So that's the integral of e to the power minus n is 1 over n. And to get the x to the third outside, you just perform derivative 3 times, so you get 1 over n to the fourth. Was I clear, or should I write it?
Can you write it, please?
Sure. So, sidebar. Hope this is understood. can derive both sides by dot to the n. What will I get here?
There shouldn't be an N in the left side.
Okay, of course not. Okay. So 1 power is 1 over n square, like minus goes. Do it twice, you'll get 1 over n to the third. Do it twice, so x to the 3, you'll get n 1 over n to the fourth. And you'll have your numerical constants that okay. And that is a series that Euler has already summed up.
Now the real numbers with pi, wait, pi to the 4th over 90.
Exactly. Actually, there's a whole summation. Okay, I care here only on one thing about this expression.
The power of t?
T to the third. Remember, what was a classical solution? No.
E to the minus 1 over 6.
No. What is the heat capacitance of
שלוש מ-KB.
3 KB.
a constant? 3 nk k, because t falls off in the derivative. T goes to 0, doesn't change anything, right? It has a finite heat capacity at 0 temperature. This tells you that as T goes to 0, the heat capacity
Also goes to 0.
also goes to 0. So it's a huge difference. At close to 0 temperature, the heat capacity, due to the fact that we're dealing here with a quantum system, is completely different. But completely. It is as it tells you, sorry, I have at very low temperatures no degrees of freedom to accept energy. What does heat capacity at the end of the day mean?
כמה אנרגיה צריך להשקיע כדי להעלות את הטמפרטורה שבמערכת באחד?
And at the beginning, it's very hard to do it. So this is a radical divergence from the classical behavior. So what do I know up to now? If I'll plot CV as function of t, the classical answer, assuming I have only three acoustical modes. Per unit volume, so classical. The red is quantity. It goes up as t to the third for small t's, approaches the classical value at large t's. Heaven knows what's happening here. So in order to answer on the question, what happens between here and here, that is basically the Debye approximation. Just being to give some qualitative answer on the behavior between here and here. Actually, I must say that it's not extremely convincing, the Debye approximation. And many materials you have to go, it would have been even better just going and brute force performing this numerical integration with the aid of computers. Unfortunately for Debye, in the 1920s, the meaning of computer was a person doing the computation, not a box, a machine, and of course it's hard to perform. So he made some simplifications in order to fill up this gap. Is it really a physical theory? No, it's some kind of extrapolation between here and here. Okay. So, what are the assumptions? Three acoustical branches. Okay, as long as we are dealing with one atom per unit cell, it's okay. And even if we do more than one atom, as long as T is not too high, it's probably also okay. And here comes the crucial and somewhat questionable assumption. That is, look, anyone who was conscious during the last hour saw that this exponential type of integration gave us trouble. So the guy said, okay, let's forget about it. KD is K divide. Okay, instead of worrying about the change in occupation of these phonons as function of K, I use here a very crude approximation and say they are all filled up to some KD, they're all empty above that KD. So I won't try to convince you that it's a good approximation because it's not. I still have to have the same number of phonons. If you want your grand canonical assumptions that I have a given number of phonons, but with a crude approximation. So I say the volume within K space that is filled is the volume of degrees of freedom that I have in the system, of number of atoms in the system. Okay, at the moment I do some hybrid assumption here. I calculate the cutoff by KD, which is assuming that all the states are filled, but continue to retain the filling according to the previous behavior of the system, which we have seen. Okay, now he goes and defines the bifrequency and the bi-temperature and rewrite the integral and after performing this integral numerically, tells you that up to about 0.2 of the bi-temperature we have a behavior that is similar to T to the third. Then you have some extrapolation between these points. Okay. For me, all this doesn't add much knowledge, except that one point, defining the bi-temperature is useful in understanding the properties, because it gives you a scale for which the quantum behavior is very important. So basically, if you go and check for certain materials, you can do a table of theta debye So what's important about this table? The only thing that is important, take a fifth of the temperature here, and you'll see that basically quantum behavior is important within a range of 150 to 100 Kelvin from the absolute zero. So you have to go pretty low in temperatures, but not extremely low in order to see the discrepancy between the quantum and the classical heat capacitance. So it's a low temperature phenomena, but not extremely low temperature. Okay, questions? Okay, in the next lecture of tomorrow, which is, if you already forgot, it's held in the seminar room of the department. Not here. Don't think we had. Did we have a chance to have one?
We had one when we talked about Einstein.
Einstein, right. So it's there, and there we'll talk about another way to see these phonons. How do we actually see photons?
Quantization of the electromagnetic.
פליטות רמות אנרגיה כשאנחנו מקרינים עודף של תדירויות שונות ואנחנו מקבלים חלק מחזרה.
But how do I know it's a particle?
Photoelectric effect.
Photoelectric effect. What happens there? I have a collision between a photon and an electron that ends up in enabling conductance, or not enabling conductance in this material. So it's also a way to directly see these phonons. Until now we did only statistics. So statistics here, to what is it similar for photons?
מסות?
No. What experiment in photons was the first that gave quantum behavior?
Photoelectric.
Two-slit experiment?
No, and no. Black body radiation, which was a statistical type of measure. This is the equivalent for phonons. It's statistical behavior for heat capacity. The next lecture will see what is the equivalent experiment for phonons in order to see that we have a collision between phonons and some particle.